All right, let me remind what we did, what we were doing last time. So we continue to 5.2 and 3. Uh, 5.2, 5.3. This is about power series solution. Well, remember we had, let's recall this. We had this equation, linear equation, px y double prime plus qx y prime plus rx y is equal to 0. It's a homogeneous equation, but the coefficients are not necessarily constant. They can be non-constant functions depending on x. In that case, we say a point x naught is an ordinary point of, let's call it star here, ordinary point of this equation if q over p and this rational, this functions, not necessarily rational because p, q, r may not be polynomials, but if this functions here, q over p and r over p are both analytic at x naught. Okay. Analytic means basically the power series expansion exists and it's equal to the function. Of course, it's not easy to check from the definition. What we do is we use the fact that rational functions are analytic whenever the bottom part is not 0, or polynomials are analytic. Sine, cosine, these are analytic functions. Exponential is analytic. So we use these basic functions to determine whether a function is analytic or not, okay? Well, let's do one example with power series solution near an ordinary point, okay? So we solve the equation locally. Locally means we have a point here, okay? Let's say This is x0, and we will solve the equation in an interval containing x naught. Okay, it's like initial value problem. So the solution may not exist in the whole set on the whole real numbers, because we will have a power series. We will have a radius of convergence, right, for the power series, and this power series determine the space of the solution. Okay, so this is where we solve the system. Power series solution. Near x naught. Okay. All right, let's do one example with that. So we will solve the ODE, ordinary differential equation, y double prime minus x times y is equal to 0 around x0, which is 0. Around the origin, we will solve this equation. It's a second order equation. It's homogeneous, but the coefficient is x. Okay, so we cannot treat like a constant coefficient. In the case of constant coefficient, remember you use the characteristic equation to solve this sort of equations. But here, since the coefficient, in the coefficient we have x, we cannot use characteristic equation here. All right, let's solve it with power series solution. Well, first of all, let us check that this point is an ordinary point. For this purpose, what is PQR? Here, P is 1, right? Remember, P is the coefficient of y double prime, so P of x is 1, Q of x is minus x, and R of x is equal to 0. So we will look at Q over P and R over P. Q over P is basically minus x, and R over P is 0. And they are both analytic, right? Because x is a polynomial, minus x is a polynomial, 0 is a constant function, and we know that these are analytic functions everywhere. In particular, they are analytic at the origin 0, okay? Are analytic everywhere. In particular, at x0, which is 0. Thus, 0 is an ordinary point for this this equation, okay? x0, which is 0, is ordinary point of, let's call it here star. So we can find the power series solution since we have an ordinary point. Let's take a power series in the form of, so take y is equal to an x to the n is from 0 to infinity. We will plug this in star here and find the coefficients, okay? So that's the idea. It's very straightforward. So you will take this y, you will need a second derivative, right? Because you have second derivative in the equation, and put it back in star, okay? And plug in star. So to do that, we need second derivative. What is, let's start with the first derivative, y prime. Y prime is n times an x to the n minus 1, n is now from 1 to infinity, okay? We differentiate this again. Well, you did similar things in calculus, right? Term-wise differentiate, and then you get n times n minus 1 times an x to the n minus 2, n is now from 2 to infinity, okay? And we're going to put this back into star. So remember, star was this y double prime minus xy. So y double prime minus x times y, it will be equal to 0. Y double prime is the sum n times n minus 1 an x to the n minus 2 minus x times y. X times y is an x to the n plus 1, n is from 0 to infinity, right? You multiply y with x, you get this. This must be equal to 0. From this equation, we will find the coefficients, okay? But what I will do is I will here modify this so that we will have the same powers here and here, okay? So what I will do is I will say this is m first. If m is equal to n plus 2, I will shift the index, okay? So when you shift the index here, shifting index, then you will get what? In the first one, when you say n minus 2 is equal to m, you will get what? If n is equal to 2, m is equal to 0. So m starts with 0 to infinity. Now what is n? N is equal to m plus 2. N minus 1 is m plus 1. N is equal to m plus 2 x to the m. They are the same, right? So these two are the same. Now you do the same thing with this one now. I will say here, this is m, okay? And then do the same thing here. Minus. If now n plus m, n plus 1 is equal to m. If n is equal to 0, m is equal to 1, right? 1 to infinity. N is equal to m minus 1 x to the m. Okay, that's it. And this should be equal to 0. This is easier to work because we have x to the m in both sum. The difference here is in the first sum, m starts with 0. In the second sum, m starts with 1. We will deal with this by considering m is equal to 0 separate, okay? So basically the coefficient of x to the 0, okay? What is the coefficient of x to 0 here? When m is equal to 0, in the first sum, there is something coming, right? In the second sum, we don't have x to the 0. There is no x to the 0 here, okay? So the coefficient comes from the first sum. When m is equal to 0, it's what? It's basically 2 times 1 times, which is 2 times a, m is equal to 0, a2, right? Well, on the right-hand side here, x to the 0 is basically constant coefficient, okay? So this is a constant term. Maybe I should say here. It is the constant term in the power series, okay? The constant term in the power series is 2 times a2, but on the right-hand side, the constant is 0. That means it's equal to 0, okay? So from here, a2 is equal to 0. So let's keep it on a side. Do you have any question so far? Var mı buraya kadar soru arkadaşlar? Peki. Now we will continue with other coefficients. So the coefficient of x to the m when m is equal to, m is bigger than or equal to 1. Let's see what we get in that case. In that case, on the right hand, on the first sum, we have m plus 2 times m plus 1 times a m plus 2. In the second sum, we have minus a m minus 1. And this is equal to 0, right? So this tells you what? This tells you basically we get a recursion here, recursive relation for the coefficient. am plus 2 is equal to am minus 1 over m plus 1 times m plus 2. Okay, so we get that. Well, the nice thing is now we using this relation, we can get all other coefficients. Okay, so for instance, we know a2. What is the difference here? The difference between m minus 1 and m plus 2 is 3. That means this will define, for instance, since you know a2 is equal to 0, you can find a5, a8, and so on. If you know a1, you also know a4, a7. So you know every 3 other terms by this relation, okay? So let's start with 2. A2. A2 is equal to 0, but A5 is equal to what? Okay, A2 is equal to 0. A5, by this relation here, it's A2 over, in that case, m is equal to 3, okay? Here, maybe let's say m is equal to 3. If m is equal to 3, we will get what? We will get a5 is equal to a2 over 4 times 3, okay? Sorry, 4 times 5, sorry, 4 times 5. Anyway, a2 is equal to 0, so this is also 0. Okay, you see, a2 is equal to 0, a5 is equal to 0, and you continue this, right? And then maybe let's write here, a8, a11, okay? They are all 0. So these coefficients are 0. What about 1, 4, 7? Okay, let's check out this. So this is for 2, 5, 8. So we need to find 1, 4, 7, and so on. And finally, we will need to find 0, 3, 6, and so on. Okay. What is A1? Well, A1 is not given, but what is, let's say, from this relation, we cannot find A1, but if M is equal to, for instance, we need A4, so M is equal to 2, then we will get A4, right? A4 is equal to A1 over 3 times 4. So A4 is equal to A1 over 12. Well, A1 is, it's free. That means what? That means basically A1 can be any number, and depending on A1, you find A4, A7, A10, and so on. So next, for instance, A7. What is A7? A7 is A4 over, here M is equal to 5. So 6 times 8. Okay, or you can write better than this. It's going to be, what is A4? A4 is A1 over 3 times 4. So it's going to be 3, 4, 6, 7, 6, 8, right? 6, 8. It should be
6 çarpı 7 olacak hocam.
right. This should be 7, right? 3, 4, 6, 8. Okay. Well, you can continue with this. A10 is, in that case, it's gonna be A7 over A7 over 9 times 10. Okay, so it's gonna be A1 over 3, 4, 6, 7, 9, 10, and so on. Okay, like this. And you continue this. And A1 is free here. Maybe I should say here. A1 can be any number. It can be any number you take, okay? Well, what is left here? So we find A1, A4, A7, A2, A5, A8. So 0, 3, 6, these are these remains, right? How do you get 0? Well, M is equal to 1, right? If M is equal to 1, in that case, you will get A3 is equal to A0 over 2 times 3, okay? What about A6? A6 is equal to, again, with the same relation, M is equal to 4 now. A3 over, A3 is A0 over 2 times 3. So A3 over 6 times 5, right? M is equal to 5 here now. No, M is equal to 4. 4, M is equal to 4, so it's going to be 5 times 6. And you continue this. A9 is, for instance, A6 over A6 is A0 over 2, 3, 5, 6. Here, m is equal to 7. If m is equal to 7, then you will get 8 times 9. Okay. Well, you can continue this process and write as many as coefficients you want. Okay, but let's start with 3 of them for each sequence. So basically, you cover all this coefficients, right? Because we know A0, A3, A6, A1, A4, A7, A2, A5, A8. That means you cover the whole set of integers. Now let's combine all this. So what is now the power series? The power series is y is equal to, remember, an x to the n, okay? And here, remember, these are all 0, 2, 5, 8, okay? 2, 5, 8, 11, and so on. These are all 0, right? You see here, they're all 0. So you will get like x cubed, x to the 6, x to the 9, right? It's like, what is, for instance, n is from 0 to infinity. When n is equal to 0, a0 is, okay, a0. Next, we will have a3, which is a0 over 2 times 3 x to the 3, right? This is x cubed, a3 x cubed. Then we have a6 x to the 6, so a0 over 2 times 3 times 5 times 6 x to the 6, okay? Next, we have a9 x to the 9. Maybe let's write a9. What is a9? a0 over 3, 2, 3, 5, 6, 8, 9, x to the 9, plus you go like this. The other coefficients are, the other terms are 1, 4, 7, and so on. So let's write those. What is a1 is a1, right? a1 x plus a4. A4 is what? A4 is a1 over 3 times 2, 3 times 4. a1 over 3 times 4. This is a4 x to the 4 plus a7. A7 is a1 over 3, 4, 6, 7 x to the 7. And you continue like this. Okay. And that's it. If you want to write this in a better form, maybe let's do it. It's going to be like a0 is, remember, it's an arbitrary number here. We don't have any condition on a0 and a1. Here, a0 is also free. This is also free because we don't have any condition. If the initial conditions are given, you can find a0 and a1, but here there is no initial condition. Well, let's take this in a0 parentheses. In the first one, a0 parentheses, we will have this 1 plus x cubed over 2 times 3 plus x to the 6 over 2, 3, 5, 6 plus x to the 9 over 2, 3, 5, 6, 8, 9. So you see the pattern right here. And it goes like that. Plus, in A1 parentheses, we will have x plus x to the 4 over 3 times 4 plus x to the 7 over 3, 4, 6, 7 plus, and so, okay? So this is the power series solution near 0. Well, you can think of this like it's one solution here we have. Let's call it y1x. This is y1x. And there is another solution here, y2x. So we have two linearly independent solutions, and the general solution for the homogeneous equation is basically the linear combination of these two, right? It's like C1 times Y1 plus C2 times Y2. Here, instead of C1, C2, we have A0, A1 as constants, okay? Here, maybe say, let's say, where Y1, Y2 are linearly independent. Solutions. But anyway, this is not very important, but it looks like the earlier form of the solutions, right? You have a second order equation, you have two linearly independent solutions, and general solution is the combination of these two linearly independent solutions. Here we have a similar thing. Any question with this? It looks complicated, but it's not. Yes.
Yukarıda şu index shifting olayını nasıl yaptık? Bir de anlatabilir misiniz kısaca?
Peki, bakalım. Here we shift the index. So what I said in the first one, for instance, here. We are looking at this one, okay? In this one, we say n minus 2 is equal to m. When you say n, and maybe let's do it here. When m is equal to n minus 2, that means n is equal to m plus 2, right? So if here n is equal to 3, n is equal to 2, okay, n is equal to 2 here. N is equal to 2 means m is equal to 0, right? Because m is equal to n minus 2. 2 minus 2 is 0. So you start with 0 here for m. Now we replace all other terms. What is here, for instance, n? Okay, n is equal to m plus 2. So we have m plus 2 here. What is n minus 1? N minus 1 is n minus 1 is equal to, you take 1 off, so it's going to be m plus 1. So we have m plus 1 here. And n is equal to, in that part, m plus 2. Clear now?
Evet hocam, teşekkürler. Sağ ol.
Yeah. Any other question? Var mı başka soru bununla ilgili? All right. Well, the question is, what is the radius of convergence in that case? The solution, the radius of convergence of the solution. It's not easy to find, but in some cases we can determine this easily without using any test. So let's talk about this. So this is a fact. Maybe let's talk about this first. We can always find a power series solution near an ordinary point. So this is a fact we should know, okay? So we can always find, that means solution exists, okay? Solution exists near an ordinary point. Always find a power series solution near an ordinary point. Okay. And the question here, in what range is the power series representation of the solution valid? Okay, is the power series solution, let's say. Well, that means, okay, you find a solution near an ordinary point, x naught, okay? But how large is the interval where this power series solution exists? Okay, so that's the question. So this can be small or large. How do you determine this, right? Of course, one thing, you can check the radius of convergence of the power series. It's not very easy because we don't know the concrete formula for the power series. Look at the previous example, for instance. How do you check the radius of convergence here? It's not easy, right? But what you can do is, here it says, this is a theorem which says the following. So the question is, how big is the interval of convergence, basically, okay? How big is the interval of convergence for the power series solution? The theorem says the following. So that we have an ordinary point of the equation okay, and there is another x1. It's the singular point nearest to this ordinary point, okay? Let x1 be a singular point. Singular point means the function is not analytic at that point. Sorry, the coefficients, right? Q over P and R over P, at least one of those is not analytic at x1. Singular point of, let's call it here, this is star. Nearest to x0. Okay. Then the power series solution power series solution y x, which is an x minus x0 to the n is valid on x0 minus rho, x0 plus rho, where what is rho here? Rho is the distance from x0 to x1. Okay, that makes sense because think of like in the picture, let's say this is x1, okay? So x1 is the bad point, it's a singular point. That means function is not analytic there. And so this tells you basically you can go at most up to x1 and you have to stop there because the coefficients are not analytic there, okay? So the distance here, this is basically rho, right? The distance is the radius of convergence of the interval, okay? Interval of convergence. With this theorem, for instance, in the previous example, let us look at the previous example. We had this equation, y double prime minus xy is equal to 0. The nice thing is we don't have any singular point here. No singular point, right? Because minus x and 0, they are analytic everywhere. Since there are no singular point, the series here, valid or interval of convergence, is what here in that case?
Sonsuz.
What?
Infinity.
Infinity, good. The radius of convergence will be infinity because we don't have any singular point. You don't have to stop at some point, right? You go from 0, you go to infinity without any singular point, and to the left you go to minus infinity. So the expansion is valid everywhere on the real line. Okay, so theorem says this. You don't need to check here radius of convergence. Radius of convergence will be infinity. Okay, by this theorem. All right. Any question?
Hocam, how do we understand that whether we have a singular point or not? I guess I missed that
A
part.
singular point is basically if you have a rational function, for instance, then if the singular point is the point which makes the bottom 0. For instance, in this example, we have minus x and 0, right? This is p over q over p is minus x, and this is r over p, rx over px. Minus x is polynomial, and polynomials are analytic everywhere, so we don't have any singular point, right? This is analytic everywhere. It's a polynomial. Again, this is a constant function, so it is analytic everywhere. That means you don't have any singular point. But think of like a function like this, x over, or let's say 1 over x times x minus 1. Here we have two singular points, 0 and 1, because 0 and 1, the function is not defined, so it's a singular point, right? You cannot write the series expansion at 0 and 1 because function is not even defined at that point. So 0 and 1 are singular here in that case, okay? Singular point. So let's say you expand the series around 0. So if you expand the series around 0, there is here one, well, basically you cannot expand series around 0, but let's say you expand the series around, let's say, okay, around this ordinary point. Let's take an ordinary point. For instance, you take 3, okay? It's an ordinary point. Ordinary point. These are 0 and 1 singular points for this function. and you are going to expand the series around 3. What is going to be the radius of convergence in that case? So you start from here, you go up to the next closest singular point, which is 1. So that means the radius of convergence, this is rho here, is equal to 2. Okay, so you can expand, for instance, the series around 3 at most up to here. Make sense? Oldu mu?
Thanks hocam.
Ordinary point'ten singular point'e kadar gidebilirsiniz. Power series expansion'da. Singular point'lerde genelde fonksiyonun tanımlı olmadığı, analitik olmadığı noktalar. All right. Maybe let's give a break here. It's a good place to give a break. Let's continue at 9:40. Okay. Tekrar merhaba arkadaşlar. Welcome everyone. So before we continue, do you have any question? Well, we talk about a power series solution near an ordinary point. Now, we will talk about series expansion in some worst cases, like we don't have an ordinary point, but we have sort of half singular points, okay? And these are called regular singular points. So these are singular points, but they are not too bad, okay? And we can still find a series expansion in that case. This is section 5.4 in the book. And they are called regular singular points. Regular singular points. So let us define these points. What are these points? Well, again, we have a second order differential equation. Suppose that we have a second order linear ODE. It's px y double prime plus qx y prime plus rx y is equal to 0. So we have an homogeneous second order linear ODE. The coefficients are not necessarily constant. They can be function of x. Again, we will talk about power series solution now. But let's first talk about what's a regular singular point. So it is a definition. We will define regular singular point. A point x naught is called a regular singular point. Regular singular point for, let's call it star here for the differential equation, if first it's a singular point, it's a singular point of star. That means it is not a regular point, okay? And second, when you multiply with x minus x0, this q over p, singular means q over p is not analytic at x naught, but when you multiply with this term, x minus x naught, and when you multiply the other one, remember the other one was rx over px. So you multiply this with x minus x0 square, okay? Square. Let's write it better. This and x minus x0 square, they are analytic at 0, okay? So these are analytic near x0. All right. So multiplying with x minus x0 and x minus x0 square, these two functions, we have an analytic functions. In that case, if we have this, then we say it's a regular singular point. Okay. Let's give an example of a regular singular point. Well, think of an equation like this: x cubed times x minus 1 times y double prime plus x plus 2 y prime plus 4y is equal to 0. So let's check out the singular points here. So in that case, this is p of x. Here is q of x. And 4 is r of x. Okay. So we check q over p and r over p. Q over p is x plus 2 over x cubed times x minus 1. Okay. And r over p is 4 over x cubed times x minus 1. So let us check the singular points here. The singular points are, so what are the singular points? You tell me.
1.
0, 1.
Right, 0 and 1 are singular point. Good. These are singular points. So x is equal to 0 and x is equal to 1 are singular points. Okay. Singular points of, let's say, star. Let us check whether they are regular singular points. For this purpose, we will multiply the first function with x minus, well, depending on the singular point, right? So x minus 0 or x minus 1. So let us check 0 first. At x is equal to 0, we will check this, right? X times q over p, which is x times this, okay, and x squared times r over p, and this is what? 4x squared over x cubed x minus 1. Well, the thing is here, at 0, both are singular still, right? They are not analytic. Both functions are not analytic at 0, because even if you cancel out this term, you will get x squared in the bottom. You cannot get rid of 0 in the bottom, so the function is not analytic at 0. And similar here, cancel out, and you still have 1x in the bottom. So both here are not analytic. Even if one of them is not analytic, we say it is not a regular singular point. So this tells you that 0 is singular point. Point of what? Of x times q over p and x squared times r over p. One of them is enough to say that it is not a regular singular point. That means 0 is not a regular singular point. Okay, so in that case, 0 is not it, so it is not a good point basically. Okay, it's the worst point you may have because it's singular and it's not regular singular. Okay.
Hocam,
Yes.
why it isn't regular singular point? I'm sorry, I missed it.
Because for regular singular point, we need this. Both here must be, both functions must be analytic at 0, okay? And we see that both functions here, none of them is here analytic, right? They're both singular. Değil mi? Yani şu ikisi de x eksi x sıfırla yani x ile çarptığın zaman, diğerini x karede çarptığın zaman eğer ikisi de iki fonksiyon da beraber analitik oluyorsa o noktada, o zaman noktaya regular singular nokta diyorsun. Ama burada hiçbiri şey değil mi?
Hocam ama analitikken singularlık durumu, yani regular'ın farkını anlayamadım, o yüzden
Şimdi
sormuştum.
yapacağım. Bir x1'e bakalım, orada göreceksin.
Tamam.
Okay.
Ya analitikse zaten singular point değil gibi bir durum yok mu?
Ama neyin regular'ı? Şimdi neyin analitiği? Analitikse derken
Fonksiyonun için.
bu ama x eksi x sıfırla çarptıktan sonra analitik oluyor. Yani orijinal
Evet, tamam, evet, doğru,
analitik değil.
onu kaçırdım.
Çarptıktan sonra. So after you multiply with x minus x0 and x minus x0 square, it's analytic. In that case, you say it is regular singular point. Okay, it is still a singular point, but it is not much singular, I would say. So let us look at the other point. X is equal to 1. At x is equal to 1, we have a singular point. Let us check whether it is regular singular or not. So for this purpose, we will multiply q over p with x minus 1. X minus 1 times q over p. So it becomes what? Q over p is this. X plus 2 over x minus 1 times x cubed. Now you multiply this with x minus 1. Well, the nice thing is you can cancel out x minus 1s, okay? And it becomes an analytic function, right? So when you multiply with x minus 1, you get rid of x minus 1s, and then the remaining here, x plus 2 over x cubed is analytic at x is equal to 1. So this tells you basically this is analytic at 1, which tells you that x is equal to 1 is, well, you need to check the other one as well. Sorry, we should check both, right? The other one was, remember, you multiply with x minus 1 square, which function? R over P. R over P. R over P is 4 over x cubed times x minus 1. 4 over x cubed times x minus 1. And you multiply this with x minus 1 square. Well, again, you cancel out the terms here, this one with one of those, and still you see that the bottom is non-zero. So this is also analytic at 1. If both are analytic at this point, then you say that 1 is a regular singular point of the original equation, okay? So this tells you that x is equal to 1 is a regular singular point of star. Is it clear what we are doing here? So 0 and 1, they are both singular points, but 1 is better because at 1, after you multiply with some terms, you make your functions regular or analytic. So you say it's regular singular point. 0 is the worst type of singular point. You cannot make it regular singular, okay, at 0, but at 1 we are fine. So what is the purpose of this? Well, now we will talk about the power series expansion around regular singular points. We can find the solution around regular singular point, like in the case of regular points, okay, ordinary points. All right. Let's write this as a remark. So a regular singular point is a well-behaved singularity, is a well-behaved singularity, and power series solution can be it says power series solution method, let's say, works with some modifications, okay, with some modifications. Well, still you can find a power series solution like in the case of ordinary point for regular singular points. But we need to modify the solution. It needs a little bit more work, okay? So for this purpose, we will talk about first Euler equations. What's an Euler equation? Well, let's define this first. Definition. Well, an equation of the form, it's like this: x minus x naught square y double prime plus alpha times x minus x naught y prime plus beta times y is equal to 0. Here, alpha and beta are real numbers, where alpha, beta are real, is called an Euler equation. Again, it's a non-constant coefficient second order linear equation, but the coefficients are in some certain type. The coefficient of the second derivative here, y double prime, is x minus x0 square. The other one is like x minus x0 and so on. So it's in some certain type. And in that case, we modify this equation. And after we modify, we will get a constant coefficient equation. And you know how to solve constant coefficient equations, right? How do you modify this? first of all, you may realize that x0 in this case, it's a singular point, but it's a regular singular point. Maybe let me give this as an exercise. You just apply the definition, check the definition of regular singular point. So let's call it star. Check that x is equal to x naught. This point is a regular singular point. Okay. Well, to solve this equation, we will change the variable. So we will say to solve star. The trick here is you will say replace or substitute x minus x0 by e to the t. So t is the variable now. Instead of x, we will use t as a variable. Okay, independent variable will be t. Then let's see how we can replace this. We need the derivative of y in terms of t. What is derivative of y? Well, you can think of y as a function of x, and x also depends on t. So this is like dy dt, dy dx, sorry, dy. Or you can think of like, okay, we will write everything in terms of t. So let's do it like this: dy dt times dt dx, right? Because we need to find derivative of y with respect to, well, this is originally, this is dy dx, okay? And we need dy dt, we need this one. But what is dt dx? Dt dx is, you can find maybe here, dx dt, derivative of x with respect to t, it is basically e to the t, which implies dt dx is 1 over that, right? 1 over e to the t, which is e to the minus t. So let's put this back in here, and maybe let's keep on a side. So this is going to be now what? This is going to be dy dt times derivative of t with respect to x, which is e to the minus t. We just find out here, right? This is y prime. What about y double prime? So we do the similar thing for the second derivative of y. This is basically derivative of y prime with respect to x, dy dx. So you can think of this like, first with respect to differentiate with respect to t, this dy dx. Dy dx is dy dt e to the minus t. We take this here, okay? Times dt dx. Chain rule. Well, dt dx is, again, it is e to the minus t. Oh, sorry, this is x. This is e to the minus t, okay? So from this, we get what? We get basically, we use the product rule here, d square y dt square e to the minus t plus dy dt times derivative of e to the minus t is e to the minus t times minus 1. So there's going to be a minus sign somewhere here. E to the minus t. And you multiply the whole thing with e to the minus t. So multiply the whole thing with e to the minus t. And you get basically e to the minus 2t parentheses, we have d square y dt square minus dy dt. Okay, so this is the second derivative. Remember, it was y double prime in terms of t now. So you will plug this back in here, the equation. What was the equation? X minus x0 square. What is x minus x0 square? X minus x0 square is here. This is x minus x0, and it's e to the t. So when you take the square, it's going to be e to the 2t. So maybe let's, okay, it's a star. So plug into star. So it's going to be e to the 2t. This is x minus x0 squared times y double prime. Y double prime is, right, it's y double prime is here. E to the minus 2t d square y dt square minus dy dt. So this is one thing. Plus, next, it's alpha times e to the t y prime, right? So this here, we are now at this point. Alpha times x minus x0. X minus x0 is e to the t. Alpha times e to the t times y prime. Y prime is, where is it? Here. Dy dt times e to the minus t. Dy dt times e to the minus t. Okay, good. Finally, the last part is beta times here y. Beta times y is beta times y, right? Because there is no x here. Beta times y is equal to 0. All right, well, let's organize this. So you multiply e to the 2t with e to the minus 2t, so you will get 1, basically. And nice thing is you get such a simple equation, d square y dt square, second derivative of y, basically, with respect to t, minus dy dt, but there is also here, oh, we cancel out this one with that one, okay? So we have minus dy dt plus alpha times dy dt. That makes alpha minus 1 times dy dt. So we get this plus alpha minus 1 times dy dt. And finally, we have beta y is equal to 0. And this is a constant coefficient differential equation. The coefficients are constant now, so we can easily find the solution using characteristic equation. So you see star, when we modify star, when we replace x minus x0 by e to the t, we get a constant coefficient equation. It's a constant coefficient ODE. All right, we try to solve this. So let's call it double star here. To solve double star, we look at the characteristic equation, which is lambda square plus alpha minus 1 times lambda plus beta is equal to 0. Well, we will find the roots. Remember, you find the roots, right? So the roots are basically, you use the quadratic equation. First of all, we find the discriminant. Discriminant is alpha minus 1 b square minus 4 times a times c, which is 4 beta. Okay, so you look at the discriminant, and depending on the discriminant, we may have different sort of solutions, right? If, for instance, discriminant is positive, that means you have 2 real roots. In that case, you write the solution, right? So case 1, let's say, delta is positive. In that case, we have 2 distinct real roots. So there are 2 distinct real roots. Say, for instance, R1 and R2, right? And what is the solution? Then the solution is general solution. It's going to be y is equal to C1 times e to the R1 t plus C2 times e to the R2 t. Well, this is the solution of the second star, right? With respect to t here. This equation. This one. But we would like to solve the first equation. But first equation is equivalent to the second equation under this here replacement. So we replace x minus x0 with e to the t here. So what I'm going to do is, instead of e to the t, I will write x minus x0. So this is equal to, under the change of x minus x0 is equal to e to the t. Okay. C1 times, so you can think of this as like e to the t to the R1, right? But e to the t is x minus x0. So it's going to be x minus x0 to R1. Okay. And plus C2 x minus x0 R2. That's it. So this is the form of the solution of the Euler equation. Solution. Maybe I should say here that when we write like this, e to the t is positive, okay? E to the t is exponential function. It is always, this is always positive, right? That means basically here we consider the case when x is bigger than x0. So we find the solution on this interval when x is bigger than x0. So here we consider the case, this is x0, and we consider the case of the solution when x is bigger than x0. So on this interval. We will also need to look at this part. It's similar. What you do is for that part, you consider the replacement with minus e to the t, okay? So you will get a similar thing basically. Well, I don't really like these colors, yellow and red. Let's make it. This and this, okay? So we also consider left-hand side of x naught, okay? The other side of this point. Well, in that case, we will get a solution, general solution with the negative of this. So that's why we need to consider the absolute value, but we will talk about this later, okay? Solution of, okay. Solution of Euler equation when x is bigger than x0, okay? In the case of delta is positive. Well, let us check other cases. So when delta is equal to, for instance, 0, what we get is case 2, delta is equal to 0. In that case, we will have two real solutions, but same, right? Well, actually one real solution, repeated one. So R1 is equal to R2 is equal to same number, R. So the general solution will be y is equal to C1 e to the R1 t plus C2. Remember, or maybe RT, let's say RT because they are same. In that case, we multiply the solution with t, right? When you have repeated root, t times e to the RT, okay? But let's write it everything in x. So it's gonna be what? It's gonna be C1 times, again, here e to the t is x minus x0 to the r plus C2 times, well, let me remind here on a side, x minus x0 is equal to e to the t. That means t is equal to ln x minus x0, okay? Logarithm x minus x0. So that's why we have here ln x minus x0 e to the rt is again x minus x0 to the r. Okay. We have this as a solution when you have a repeated root, when delta is equal to 0. Well, finally, we have delta negative, case 3. In that case, delta is negative. We have complex solutions, right? Roots are complex conjugates. So we have R1 is A plus BI, and R2 is the conjugate of this, A minus BI, okay? And in that case, remember the solution is basically the real and imaginary part of the complex solution, which are e to the C1 times e to the A t times cosine bt plus C2 times e to the AT times sine bt, right? The first one is real part, second one is imaginary part, so the combination gives you the general solution. Again, we return to the original variable x, so y is equal to C1 e to the AT is x minus x0 to the A, okay, cosine bt. Cosine bt is cosine b times, remember t was ln x minus x0. This is hard to memorize, I agree. Okay, so this plus C2 x minus x0 to the b, and you will have sine b of yeah, there's another here parentheses ln x minus x0, this, okay? So this is the general solution when we have negative discriminant. All right, any question with this?
Yani ben bir soru sorabilir miyim?
Tabii.
Şimdi mesela çözmeye çalıştığımız equation'lar p çarpı px çarpı y'nin ikinci türevi artı qx çarpı y'nin türevi artı r eksi eşittir 0 şeklindeydi.
Şunu diyorsun değil mi? Evet,
O zaman
baş...
şimdi burada
evet.
burada o zaman regular singular point'te buradaki px'imiz bizim her zaman x eksi diyelim 3'ün karesi gibi bir şey olmak zorunda.
Evet, tabii. Hı -hı. Evet,
Hayır.
buradaki şu senin p oluyor o durumda. Burası q oluyor. Bu da r. R sabit. Beta.
Yani burada yani q bölü p'miz mesela 1 bölü x eksi x0 oluyor. Burada da x0 analitik olmuyor.
Evet.
Sonra bunu x eksi 0'la çarptık. Bakalım bu şekilde oldu mu diye. O zaman analitik oldu.
Evet, çünkü o da götürdü değil mi? Bir tane.
Evet, evet. O zaman analitik oldu. Sonra
Diğeri,
da
diğeri de aynı şekilde beta'yı böldüğün zaman.
evet. Sonradaki bu solution'ları örnekte daha iyi görürüz ama
Evet, yapacağız.
tamam,
Yani
tamamdır hocam.
bununla ilgili örnek yapacağız. Maybe let me conclude this part with a remark. In the case of x, so here we consider x is bigger than x0. If x is less than x0, you will do the similar thing. Okay, let's write this as a remark. On the interval, minus infinity to x naught, that means basically that is x is less than x0. We use the substitution. X minus x naught is equal to minus e to the t. Instead of e to the t, we use minus e to the t. And in the solution, for instance, we have x minus, look at this. In the solution, we have x minus x0 to the a, right? But now it's going to be minus of this. So in the solution, replace, it's going to be, instead of x minus x0, it's going to be x0 minus x. So in general, we can replace in the solution x minus x0 by absolute value of x minus x0. Then this will cover both cases at the same time, even when x is bigger than x0 or x is less than x0. The absolute value of x will take care of both cases. Okay. For example, when delta is positive, remember, this is the case 1. In the first case, the solution becomes, in general, whether you have x is bigger than x0 or x is less than x0, the general solution you can write it in this simple form. In absolute value, R1 plus C2 in absolute value to the R2, okay? All right, any question with this? We will do some examples on Tuesday. And we will see how we can use this in power series solutions, okay? Right now, we haven't talked about the relation between the power series, but this will play an important role in the solutions of power series near an ordinary singular, regular singular point, okay?
Hocam yani bir şey sorabilir miyim ben?
Evet.
Şimdi o zaman bu Euler equation'da aslında second order böyle constant coefficient olmayan işte differential equation.
Evet.
Bunların çözümlerini bulduk şimdi.
Bulduk, evet.
Ama şu anda kullanmadık.
Power series
Serileri
kullanmadık.
kullanmadık.
Evet, çünkü bu çok özel bir durum. Yani işte bunun çünkü katsayıları işte x eksi x0, x eksi x0'ın karesi. Hani bunlar çok böyle değil mi? Çok özel bir formda. Dolayısıyla power series'i kullanmadan yapabildik burada. Güzel analitik bir çözüm bulduk. Yani tam olarak hani böyle power series çözümü, çünkü çok böyle elle tutulur bir çözüm de değil aslında. Çünkü birkaç koeficient'ı biliyorsun. Gerisini böyle hani elle yazmak falan çok mümkün değil hepsini. Ee, Ama bundan sonraki aşama şu olacak. Ee, Daha genel regular singular pointler etrafında hani o katsayılar bu kadar özel olmadığı zaman, çok daha genel fonksiyonlar olduğu zaman buna benzeteceğiz. Yani Euler equation'e benzeteceğiz. Ondan sonra bu Euler equation'dan elde ettiğimiz sonucu kullanıp sonuca varacağız.
Tamam. Seriler içerisinde daha böyle özel Euler equation'a indik. Böyle seri
Evet,
çözümleri
evet.
yapılabilen denklemlerde daha özel denklemlerdeyiz şimdi.
Daha özel bir denkleme baktık. Euler equation'a baktık. Onun için power series'e gerek kalmadı. Çünkü bu çok özel bir denklem. Yani bunun katsayıları çok hani bilindik katsayılar. İşte birine diyorsun ki x eksi x sıfır olsun. Diğeri onun karesi olsun. Ama daha karmaşık, daha genel fonksiyon olduğu zaman katsayılar bu fikri kullanamazsın. Yani bu böyle değiştirdiğin zaman bu kadar güzel çıkmaz. Hani e, üzeri t dedik ya şeye x eksi x sıfıra falan. Hani bu katsayılarımız güzel olduğu için böyle çıktı. O zaman da işte power series kullanmamız gerekecek.
Bir dahaki yani derste power series
Evet.
ve Euler equation çözümleriyle beraber
Aynen, aynen. İkisini birleştirip çözüme varacağız. Evet.
tamamdır.
Alright.
Çok
Any other
teşekkür.
question? Hı-hı. Okay, let's stop here. See you on Tuesday.
Hocam bir
Bye.
şey daha sorabilir miyim?
Sor.
Bunları böyle bu çözümleri bir şekilde böyle el alışkanlığımız olsa iyi olur değil mi? Her case
Tabii
için.
yani evet yani bu mesela
Çözümleri bilsek sonucu denkleme bakıp bir görsek
evet.
iyi olur.
Çünkü burada mesela hani bu kadar işlem yaptık ama aslında şu formu bilsem hani diyelim ki delta büyüktür sıfır durumunda. Burada mesela what is here R1 and R2? R1 and R2 are basically the solutions of this characteristic equation. Here alpha and beta, remember, are the numbers coming from the original Euler equation. Yani değil mi? Euler equation'da alfa ve beta'yı direkt şurada karakteristik denklemde yerine koy. Oradan R1, R2'yi bul. Buradan da solution'ı yani direkt yapıştırabilirsin. Hiç uzun uzun bu şeyleri işte x eksi x sıfıra e üzeri t demek falan bunlara gerek kalmaz. Bunu yapabiliriz.
Tamam anladım hocam sağ olun.
Peki. Görüşürüz o zaman. İyi bakın kendinize.
İyi günler hocam.
Görüşürüz hocam.